We're going to determine if the series, the summation from 1 to infinity of n squared plus 3n divided by the square root of 2n to the fifth plus 4n squared plus 5 converges or diverges. And we're going to use the limit comparison test, abbreviated from this point on by LCT. Here's how this test works. Suppose we have two series, one we call the summation of a sub n and the other the summation of b sub n, with the restriction that an and bn must be positive for all n. If the limit as n approaches infinity of an over bn is equal to L, and this L, this limit L, is positive, can't be zero, and finite, then the following must be true. Either the series a sub n and the series b sub n both converge, or the series a sub n and the series b sub n both diverge. We can have an series converging and bn series diverging and vice versa. So let's use a limit comparison test on our series. We always denote the series we're trying to determine if it converges or diverges by the a sub n series. So let the a sub n from summation from 1 to infinity, a sub n, be our series n squared plus 3n divided by the square root of 2n to the fifth plus 4n squared plus 5. Now the question is, how do we determine what should the b sub n series be? Well, before we select it, we want to modify or express the series in a simpler way that will make the selection of bn easier. And here what we're going to do is factor the highest power of n from the radical in the denominator. So we'll rewrite this as the summation from 1 to infinity of n squared plus 3n, and in the denominator, inside the square root in the denominator, we'll factor out highest power of n that's there, which is n to the fifth. Then it leaves 2 plus 4 divided by n cubed plus 5 divided by n to the fifth power. We can easily check by multiplying 2 plus 4 over n cubed plus 5 over n to the fifth that is in fact 2n to the fifth plus 4n squared plus 5. And now one more step, we can now take the square root of n to the fifth and rewrite this as the summation from 1 to infinity n squared plus 3n divided by square root of n to the fifth would be n to the 5 halves times the square root of 2 plus 4 divided by n cubed plus 5 divided by n to the fifth. Now notice that inside the square root, as n gets larger and larger and larger, 4 over n cubed, 5 over n to the fifth, they get smaller and smaller and smaller, so they become negligible when n is very large. We want to now look at the highest power of n we see in the numerator and denominator. We'll start with the denominator we call d, the highest power of n, and that is 5 halves. We call n the highest power of n in the numerator, that's 2, and now subtract n from d. So 2 subtracted from 5 halves is equal to 1 half, and that is going to tell us what the choice for the second series, the b sub n series, is going to be. It's going to be the simplest series such that the difference in the highest power of n in the denominator and the highest power of n in the numerator is 1 half. And of course such a series is summation from 1 to infinity of 1 divided by n raised to the 1 half power. Okay, let's make sure that this limit an over bn is in fact positive and finite. So the limit as n approaches infinity of an divided by bn is equal to the limit as n approaches infinity, n squared plus 3n divided by, in that simplified form, n to the 5/2 times the square root of 2 plus 4 over n cubed plus 5 over n to the 5th, and then divided by bn, which is 1 divided by n to the 1/2. Now this has the effect of taking n to the 1/2 and multiplying this numerator by that, and so that's going to increase the power of n in the numerator by 1/2. This is equal to limit n goes to infinity, n squared times n to the 1/2 is n to the 5/2, that's what we want, plus 3 times n to the 3/2, and this is divided by n to the 5/2 times the square root of 2 plus 4 over n cubed plus 5 over n to the 5th. And let's rewrite this as two limits just to make things a little bit easier. This is the summation n goes to infinity, n to the 5/2 plus 3 times n to the 3/2 divided by n to the 5/2 times, and the second limit is going to be the limit as n approaches infinity of 1 over the square root of 2 plus 4 over n cubed plus 5 over n to the 5th. Now this first limit here, since the highest power of n in the numerator and denominator are the same, 5/2, that limit will be 1. And the second limit, as n goes to infinity, 4 over n cubed plus 5 over n to the 5th go to 0, and so we end up with 1 divided by square root of 2 as our limit. Clearly this is a positive number, and of course it is a finite number. So now the conclusion of limit comparison test holds. Let's bring our two series, let's write them here. Here's our an series 1 to infinity in the original form, n squared plus 3n over the square root of 2n to the 5th plus 4n squared plus 5, and then the bn series, n equals 1 to infinity, 1 divided by n to the 1/2. Well, we recognize the bn series as a p series with p equals 1/2. That of course is less than 1, and that means that this p series diverges. So this series diverges, and by limit comparison test, our series a sub n, which is the series summation 1 to infinity n squared plus 3n over the square root of 2n to the 5th plus 4n squared plus 5, must do the same thing. So we conclude now that this series also diverges, and the reason by the limit comparison test. For more